In this video, we're going to go ahead and keep talking about points of inflection and intervals of concavity. But in this case, we're going to go ahead and take a look at a couple of examples. And the first one is, I say relatively simple. I mean, some students look at it, this is kind of tough, and you know what? It kind of is. So let's go ahead and take a relatively simple example. All right, so as we go, points of inflection would occur if they were in fact points of inflection wherever the second derivative is equal to 0. And concavity is determined, as we've learned before this. If you want to see the video on the test for concavity, the intervals, or you can determine that through whether or not the second derivative is positive or negative. And so the points of inflection actually become a point where the concavity changes sign, or the second derivative changes sign. So let's start with this one. And so we take the first derivative of this, and we're going to have 3x squared minus 12x plus 12, and this is all just following our power rule for the derivatives. And then we're going to go ahead and take the second derivative, which is not doing nothing more than taking the derivative of the first derivative. So we have 6x and then minus 12. Okay, so if we have points of inflection, we must occur where the second derivative is 0. So for our points of inflection, or possible points of inflection, these don't have to be points of inflection, but they will, if they are, then they will satisfy this. So we have 0 is equal to 6x minus 12, and so if it is, then x is equal to 2, and that is our test point for possible point of inflection. Now, the secret to this, don't tell anybody. The secret to this is just to test on either side of all the points of inflection or possibilities. All right, so I'm going to go ahead and test f double prime of 1. So that's going to be 6 times 1 minus 12, and that's going to give me negative 6, which is less than 0. In other words, on the left side of 2, we have concave down. This is concave down. And then if we take a look at an example to the right, then we choose x is equal to 3. And so we have 6 times 3 minus 12 is equal to positive 6, which is greater than 0. And so this is concave up. Concave up. Now, because the concavity changed signs, then the point x equals 2, or that value x equals 2, is a point of inflection. And so now we can go ahead and say confidently that our point of inflection, we have one at x is equal to 2. Also, we are concave up, and we are concave up at 3, and so we're going concave up from 2 to positive infinity. And then we are concave down from negative infinity up to 2. Notice we're not including 2 as the endpoint, because at 2 it's 0, and it's neither concave up nor down. Okay, so now the question becomes, what does this point of inflection really stand for? And if you look at it in terms of the second derivative, meaning the derivative of the derivative, the first derivative tells you that whenever it's 0, that you have a relative min or max, or a possibility of one of the two. And so if you have a point of inflection in between those relative mins and maxes, that's the point where your slope is the greatest. And so after that, your slope tends to die off, either more positive or more negative, depending on the concavity. And so at that point, you have the greatest slope. Now, physically, what does that mean? In terms of cars, let's say, if you have a function that models how fast a car is going at a particular time, then what you can do is you can look at this, you can look at the curve, find the point of inflection, and at that point of inflection is the time of maximum acceleration. And so you can check the conditions on the car and see, okay, well, what gave us the most acceleration? And then you can use that information to determine how you're going to gear the car for fastest acceleration and that sort of thing. And so that's a fairly good use for it. We're going to end that video right here, and then we'll pick up on a more difficult video next.